Okay. So this session is being recorded. So it's a great pleasure to have Professor Castro Neto here today talking to us. Professor, I will do a reverse presentation. Professor Castro Neto nowadays is director of the Center for Advanced 2D Materials and co-director, together with the Nobel Prize winner, Professor Novoselov, of the Center for Functional Intelligent Materials, both at the National University of Singapore. He's also a distinguished professor in two departments, the Physics Department and the Material Science and Engineering, and a professor at the Department of Electrical and Computer Engineering. His journey started at Unicamp, where he got his bachelor's in 1988. It was there that we met and became friends. He got his PhD in 94 at Urbana-Champaign in USA. He did a postdoc at Santa Barbara, 94, 95. And then he was an assistant professor at UC Riverside in California from 95 to 2000. And he was a professor at Boston University from 2000 to 2008. And then since 2008, he's the director, as I mentioned, of the Center for Advanced 2D Materials. And today, and I will not talk about the many prizes and distinguished positions that he has had during his career, because this will take too much time. The title of his talk today is Microscopic Theory for Ionic Motion in Solids towards a solid-state battery technology. So, Professor Castro Neto, it's a pleasure, and I thank you very much to accept the invitation, and the microphone is yours. Wait, I have to make you into a presenter. We were here talking, so now you are a presenter, so you can share your screen. And as we did yesterday, please share your entire screen, which is works better for this platform.
Okay.
Okay.
So first
of all, here.
Yeah.
Okay.
All right. So first of all, I want to thank Professor Jorge Martins for the invitation to speak today. You know, many people may know, some people actually, not many, may know that I've been working on graphene and 2D materials for many years. But recently I've changed my attention, my personal attention, to the issue of ionic motion in solids, for the simple reason that I think that's something very interesting from the theoretical, experimental, and applied point of view. And I want to tell you a little bit about that. I'm not going to give a technical talk. My idea is to talk a little bit about why this is an interesting issue and where it comes from. So if you go back in time, the history of batteries, it's a very old one. A battery, in principle, the battery is a very simple device. You have a cathode, an anode, then you have an electrolyte, and then essentially as ions move in one direction, the electrons move as well. So essentially this ionic motion, which is a motion of ions, essentially produces an electric current. And this is the basis of all batteries, even solid-state batteries. So these ideas, of course, go back to Napoleonic times. So this is a painting of Alessandro Volta showing one of the first batteries to Napoleon. So, you know, we're talking about a few centuries, and, you know, one might wonder what's new about batteries, since this is such an old topic and has been around for such a long time. Of course, one of the reasons why this topic is so important nowadays has to do with sustainability and global warming and the green use of energy. So because everything is moving from fossil fuels towards electric. So this is a big issue. And in fact, if you look at the news, it seems that the world is very excited about this. You know, pretty much the United States now is investing billions of dollars in development of batteries. China has been investing for quite some time in batteries as well. There is a real race to develop better batteries, more efficient, fast charging, and so on. And all around the world, this is becoming very, very big. And this race will only accelerate in the next few years. So for instance, here's some news about lithium iron phosphate batteries. Again, Ford is working with CATL, which is also a company that produces these batteries. So definitely there is a huge amount of interest, economical interest, and also societal interest around these batteries. And this is an example of, you know, this lithium iron phosphate batteries. And people are always talking about replacing one type of battery by another because they cost less, they are safer, blah, blah, blah. So there is a lot of hype around this because there is a lot of money around this. And of course, one of the big problems with electrochemical batteries is the issue of safety. So this is a video from the YouTube, which I find very interesting, and I want to show to you, illustrating the dangers. So you see, this is a pretty serious issue, and in fact, we hear news of cars being destroyed by fire because of the explosive nature of liquid-based batteries. Essentially, if you put these batteries, you open up, the metal comes out, there is water, there is moisture or something. Definitely, it's a big issue, especially now that the world is going in a big way in this direction. So safety will become an even bigger issue as we move along. And this is where the solid-state batteries have been playing a big role, and there is a lot of discussion about them. Again, they structure, from the device perspective, it's quite simple. So again, you have the two electrodes, a cathode and an anode, and then the electrolyte, instead of being a liquid like in traditional batteries, it's a solid. And one of the constraints is that, first of all, this solid should be able to conduct ions, but it cannot conduct electrons. So it has to be an electron insulator, but an ion conductor. And, you know, you might wonder, you know, of course, electrons are tiny particles, ions are big particles. So how can you get that? But in fact, there is a huge family of these compounds which have this characteristic that you have ions which are free to move and electrons cannot move around. Of course, since you're talking about a solid, you might wonder, how can an atom, right? So an ion is just a charged atom. How can an ion move? If you look, for instance, at the, you know, the preferred choice for batteries these days, like lithium, right? So when you ionize lithium, its radii change from 1.5 angstrom to 0.7 angstrom. And this is pretty small compared to macroscopic scales, but crystals essentially have atoms in that scale. So it's in the atomic scale, you know, even something which is less than an angstrom can actually be quite big. And the question is, how can you make these ions move freely, right? So because there is the issue of size. And what affects the motion of these ions? After all, you have also, in solids, you also have electrons. And these ions, they will interact with the crystal structure, with the cores of the atoms present in the crystal, and also with the electrons, which are there. So one important question for us is that, is this motion purely classical? Because, you know, one might argue that a 1 angstrom object pretty much should behave like a classical object. Or is it quantum mechanical? Is there any quantum physics in this? Of course, in traditional electrochemistry, quantum physics plays a very weak role. But, you know, in solids, and this is what I want to show you, actually quantum physics actually starts playing a big role. So although the ions are almost classical objects, quantum mechanics actually plays a big role in the way ions can move in solids. And this was one of the surprises of our research, that we found that. So talking about solid state batteries. So solid state batteries are also part of the hype that is going on right now in the world. So this is a company called QuantumScape that was started at Stanford University. So this company is worth billions of dollars right now. And in fact, they don't even have workable battery yet. They went to IPO to become public even before having any sort of workable battery. They are promising the battery in the next few years, but so far we have not seen a product. And again, you know, the way they describe their battery, essentially they have this structure of anode, cathode, and then the electrolyte is not crystalline. Is made out of several polycrystalline structure. They don't tell you what exactly they have there in the electrolyte, because this is the heart of the problem, is where they are going to make their money. So And the question is, will this work? What's the basis for which you can make something like that, right? So, I am a big believer that you have to know the science very well before you can actually produce a technological product. You need to understand, the basic principles of how this works. And of course, they have big plans for their company, and that's why they keep their shareholders interested in buying their stock. There are other companies. This is another company as well, where they also propose a solid state battery based on ceramics. So essentially, you have again the cathode, the anode, which is a composite material, and a ceramic electrolyte. And of course, there is a lot of hype about this without very little scientific information about how this battery works, right? And this is another company, Solid Power, which and again, these companies are being very heavily funded. So QuantumScape got $400 million from Volkswagen. Of course, all the car companies are competing with Tesla to become the big electrical car company of the world. And again, what you can learn is like more of the same without a lot of physical content, a lot of beautiful pictures, but not so much depth in terms of the science of what's going on. And my gut feeling is that they really don't understand what they are doing. Maybe I'm being too tough on these companies, but I have the feeling that the way they are doing this is by trial and error. And if you look at the literature, especially if you are a solid state or a condensed matter physicist, and you look at a literature of batteries, it's all based very much in trial and error. So you take combinations of materials, you cook them, and then you get something, you measure some property like the conductivity, and then you make a big fuss about it. But, in reality, there is very little understanding of the basic principles that govern this. And this is quite the opposite of electronic materials, because in electronic materials, we understand very deeply what goes on. The electronics industry has an enormous degree on the properties of the materials. And so I would say, if you could compare, maybe the comparison is not perfect, but if you could compare with the semiconductor industry, it's equivalent to the early days of the semiconductor industry, maybe the 1950s, when people were still trying to understand semiconductors. I think that that's where we are for solid state batteries these days. And again, this is an example of a ceramic type battery. Clearly, these are not crystalline systems. So these are, in this case, you have these crystallites immersed on a sort of glass amorphous structure. And then you have grains, so it's extremely granular. And, as I said, from the point of view of solid state, this is highly uncontrollable. Okay, because essentially you are dealing with a amorphous system, and the ions are moving from crystalline phases to glass phases through, boundaries and all this. And obviously, this is highly uncontrollable. And then you can see that many of these experiments are not really reliable or repeatable, exactly because of the nature of the materials that they use. So, for instance, this is an example of the conductivity of one of these ceramic materials. And, you know, the conductivity goes all over the place. It's heavily dependent on how you cook the material, the annealing times, the crystallization temperatures, and all these things. So, of course, from my perspective, being a scientist, I find that very unpleasant, so to say, that, you know, that in solid state physics, we try to start from the best material you can get. And of course, once you understand the best material, then you add disorder, you add granularity, you add all these things that you don't like because you want to describe the real material. But, you know, without even knowing how the crystals behave, it becomes very hard to understand how a disordered material like that actually works. And of course, when you look, for instance, as I said, at these conductivities of these materials, it's all over the place. It doesn't seem to have a sort of underlying logic, or, you know, at least a sort of classification, a good classification of of these materials. Of course, you can see here, as I was showing, they take, for instance, lithium, silicon, phosphor, sulfur, chlorine, and put together in different amounts. They cook that, they get something, they measure something, and then that's it. This is the result. So, you know, for us, it's more like, how can we actually put some rationale behind this, right? So how can we predict what kinds of materials will be the best electrolytes for solid state batteries? So it's, when I started reading and looking at this, I felt very unhappy, and I decided that I needed to contribute to this field and try to understand exactly what's going on. So this is the paper I'm going to talk about. As you can see, I'm the old man in the chair, but I've been working with these very bright young people, Alexander, Kay, and Alexandra, on this project. And there are more people but working on this. But I want to talk about this particular paper, which we are all very proud of. And you can see from the title that, you know, this is a microscopic theory of ionic motion in solids. It's almost like a title from a paper from the 1950s, but for electrons, right? So it's exactly what I said before. I feel that that's where we are. So a title like this is, you can only write in a field that is still is being born. And so let me talk about this, because I think this is quite interesting. So I'm not going, as I said, this is not a technical talk. If you are interested, you can go to the paper. I just want to give you the theoretical ideas behind this calculation, okay? So you have a taste for it, but not necessarily technical knowledge of it. So essentially the idea is, it starts that in these materials that we're talking about, you have mobile ions and you have ions which do not move. So there is a sort of framework of ions which is fixed when the, say, lithium atoms move. So you can separate mobile and immobile ones. The ions are still much heavier than electrons, because one proton is 1,000 times heavier than an electron. And of course, there are many protons, neutrons, and electrons in these ions. So although the ions are mobile, the electrons are way faster than the ions, which means that as the ion moves inside the crystal, we can consider that the ions are static during the motion of the electrons, which is known as Born-Oppenheimer approximation, So essentially, that allows us to compute everything using traditional methods of solid-state physics. The other thing is that the system is an electronic insulator, so which means that the crystal has a large gap to electronic excitations. And we assume that during the time that the ion is moving across the crystal, there are no excitations, electronic excitations happening. So the electrons adjust adiabatically to the ion motion. So again, these are all traditional solid-state concepts which actually do not apply to traditional liquid electrochemistry, okay? But they apply here. We use a very special formalism that is called path integral, Feynman path integral method, which allows us essentially to eliminate the electrons from the problem and look at the effect of the electrons directly on the ions. And then with all this, we can actually compute the interaction between the ions using traditional methods like density functional theory. So essentially, we can go back to, again, traditional solid-state physics and compute things using traditional solid-state methods. And of course, it becomes pretty obvious that the electrons play a big role, because when the ion moves in the crystal, the electrons have to adjust to the electrostatic potential of the ion. So, and then there is a recoil due to the electrons present in the material. And an approximation that we make is that during the mobile ions motion, the framework ions essentially oscillate around their equilibrium position. So essentially, they are not allowed to move freely, and which means that we can, again, treat the framework ions as from the perspective of phonons. So then we're back again to traditional solid-state physics. So you have a charged particle moving a crystal, interacting with the ions in the lattice, producing phonons, interacting with the electrons, and being essentially dumped in its motion because of the presence of electrons and phonons. Then we can obtain a description for the ions of the physics of the mobile ions only, and we take this in the semi-classical limit, because exactly these ions are semi-classical particles. So the electrons are taken care fully quantum mechanically, but the mobile are the phonons as well, because the phonons are quantum oscillations. So you have the quantum part coming from the electrons and phonons in the system, but the ion is treated in a semi-classical manner. So then we get essentially an equation of motion for these ions, which have a memory and dissipation, because as you can imagine, as the ion moves, it's interacting with electrons, with phonons, losing energy, and you go back to a problem of a dissipative particle. Okay, so this is just to give you the framework of this calculation. There is nothing here that is uncommon to the solid state person, but this is completely different, completely new from the chemistry perspective. Okay, so it's it's a completely different way to think about ions in electrolytes. So let me just plug the final equations. So maybe not surprisingly, this equation, which is essentially Newton's equation for a particle moving under a periodic potential of the lattice. So the U here is the periodic potential, essentially feels a force, which is essentially the gradient of that potential. And then you have a sort of viscous term, which is this gamma, which is the dissipation due to the interaction of the mobile ions with the electrons and phonons. You have a thermal noise, which is this F term that comes from the thermal motion of the framework ions. And then you have the electric field. So from this perspective, it's essentially what's called a Langevin equation. So it's known for a very long time, except for the novelty, which is this gamma is not a constant, but it's a matrix. Okay, it's a matrix because you have a crystal, and in a crystal, the rotational symmetry is broken. So in different directions in a crystal, you feel different dissipation. Okay, and the interesting thing about this matrix is that it comes with very simple physical elements. Rho here is the mass density of the solid. V, L, and Vt are the sound velocities in the material. So you see, it goes like, the dissipation goes like 1 over density, 1 over sound velocity cube. So the strong dependence on the sound velocity. And then you have this age operator. This age operator is called the Hessian. You know, maybe the students are not very used to the Hessian, but the Hessian is the equivalent of the Laplacian, which is the second derivative, but it's a matrix. So it means that it has components along different directions. And this Hessian is essentially what describes the anisotropy of the crystal. So as the ion moves, depending on the direction it moves, it feels a different dissipation. And this dissipation now becomes position dependent. Depending where the ion is inside of the crystal, it feels different dissipation. Now, an interesting thing about the Hessian is that the zeros of the Hessian are the saddle points of the potential. So, which means that when the ion passes through a saddle point of the potential, its motion is dissipationless. It doesn't feel dissipation. So, and of course, the overall dissipation depends on all this, right? So this is the important thing. So this essentially gives for the experimentalists a clue what kind of materials they should look for. They should go for very heavy, high density, very high sound velocity, so very high spring constant, right? So stiff material, but which has very smooth potentials in the system. Okay, so we may ask, okay, so this is like a recipe here for the electrolytes. If you look at the steady state motion, which means you forget the second derivative here, the mass times acceleration. So essentially you look when the ions are steady state, essentially you can invert this equation and essentially get the velocity of the ion in the different positions of the crystal in the presence of dissipation and the periodic potential of the lattice, and of course the applied electric field. Now, because this is a crystal, you can now go to reciprocal space, because essentially everything has the periodicity of the lattice, and you can write down essentially this equation in momentum space, just like we do in solid state physics. So it's kind of the equivalent of Bloch's theorem here, that essentially, you know, the velocity is going to have only certain Fourier components, just like you would have for the wave function of an electron in a periodic crystal. And that, of course, facilitates the calculation of these things. So you can calculate the drift velocity, which is essentially the zero Fourier component of this equation, and then you get the ion mobility, essentially, of the ionic motion. So now this matrix has to be calculated, so you have to do a DFT calculation, and you have to calculate the Hessian of the potential, and then you have to invert the Hessian, take the average, and then you get the mobility. So unfortunately, we cannot do this analytically, because these potentials can be very complicated, but we can use, as I said, DFT, and here is an example. So these are these ionic solids, silver chlorine, lithium chlorine, etc., and you can calculate these mobilities. Now you may ask, how does it compare with the experiment? I think I have convinced you that I cannot compare this with the experiment, because this is a calculation for a single crystal. So this is the motion of the ion inside of a single crystal. It doesn't take into account the disorder. It doesn't take into account the grain boundaries. It doesn't take into account all sorts of mess that you have in these materials that these people are looking at. So unfortunately, comparison with experiment is not possible yet, but we are working on it. So this is a new laboratory that we're building in our facilities at the National University of Singapore. So this is a lab that is being built together with CBMM. Of course, people in Brazil know CBMM, especially in Berlândia, because CBMM operates in Araxá, which is not so far from you. And essentially, CBMM is very interested in new types of batteries, and we're going to have a state-of-the-art battery lab, which I believe we will be able to solve many of these issues. So we're going to, we are building also a facility to grow these crystals, single crystals of these electrolytes, and we'll be able to produce, you know, state-of-the-art solid-state batteries using this new facility. All right, so let me just come to the conclusions. I think I spoke too much already. So we claim to have developed a microscopic theory for ionic motion in crystals. This is important, in crystals, not in agglomerates, not in polycrystalline samples, in crystals, okay? We find that this ionic mobility depends essentially on the lattice softness via the sound velocity and the curvature of the atomic potential. So hard materials with smooth potentials are the best candidates for high ionic mobility. It's a way to calculate in a very controlled way with modern ab initio, DFT, and molecular dynamics. We're doing, Alexandra and Kay are doing a lot of work on molecular dynamics for these batteries. So we're applying all the tools we learn in solid state theory for this. We believe that we're working on this, extending these methods to the complicated problem with grain boundaries, impurities, and all sorts of defects. But the nice thing is this: we have now a solid basis to start doing that, right? Which didn't exist before. As I said, we believe that this is still virgin land. There is a lot to be done. And I think that this is going to be extremely hot in the next few years. At least we are betting very heavily on this, and maybe in the future I can come back here and with real crystals and talk to you about what happens. All right, look, with that, I want to thank you very much for the attention, and thank you for the invitation to be here.
Thank you, Antonio, for this very nice, very didactic talk. So we are open to questions now. Does anyone either raise your hand or open your mic and make questions? I have a couple of questions. Can you give an example of a crystal that you of a compound that you have studied using this theory?
Yeah, so I think I showed this is a list.
Okay.
So these are very simple crystals. So with two elements, one is very light, another is very heavy. And, these are the mobilities that we calculate using this formula. So but we have been studying many others, but this is just a few of the ones we study. From the computational point of view, these calculations are very heavy.
Okay.
Yeah. Okay. So it's not something you do very quickly.
Okay. Yeah, I saw from the examples that you gave of the companies that had solid state batteries or compounds that they were studying, that all of them had lithium. Basically, all of them had lithium, and some of the ones that you are showing there, at least. Three of them don't have lithium.
Yes.
And it's clear that lithium, it's iodine. Lithium iodine is the one that has the largest mobility. But you have this one here with silver iodine, and it has a decent mobility, I would say. So what can you talk a little bit about that?
Yeah, so just look at the periodic table, right? Lithium is the smallest
very
ion.
Light, yeah, and very light, right?
It's the lightest ion, right?
Okay.
So that's a good reason to use lithium in batteries.
Yeah, sure,
right?
Sure.
But actually, people are studying sodium-based batteries, right? And actually, you can use silver. You can use other elements in the periodic table.
Okay.
So what determines what type of ion these companies use is based on performance and cost.
Okay.
Right? But definitely the interest in lithium has to do with that, because it's the smallest one that you can get.
Okay. And Werneck has a question. Edson?
Yeah. Can you hear me?
Yeah.
All right. Thank you, Antonio, for a very nice talk. It's kind of different, I'd say, but very, very attractive. So, my question is, can you hear me?
Yes.
Okay. So my question is regarding the that actually interesting point about the dispersionless or the dissipationless transport of ion along the zero point of potential in the crystal. So you mentioned that there are some similarities. For instance, you talked about the Bloch theorem or analogous of Bloch theorem in these materials. So I was wondering if you have some analogy between this dissipationless transport or motion and superconductivity. Could you elaborate a little bit more?
So actually, there is a class of these ionic conductors which are called super-ionic, and these are So and they are essentially usually they are very heavy on lithium. So these are materials which have a lot of lithium atoms and it have very open structures. So essentially the lithium can move with a very high mobility, still not infinity, but very high mobility through the crystal. Okay, so this, and people try to understand, but in principle, it has to do exactly with what I was saying, is that the potentials in these materials are very soft, very smooth. So essentially, the lithium doesn't feel much of a force coming from the lattice itself. Okay, so and this is what I'm saying. So, but we are still, in the search of the highest mobility. So these mobilities that I showed, you can think of them as upper limits. They can only be attained in super duper clean and crystalline systems, okay, which we hope to produce in our labs, because this is not the way the industry is going. The industry just wants to get a result that they can sell, right? But we want to go deep into the the basic science of these materials.
Okay, thank you, thank you.
So just sagging on. Well, Sergio Jova has a question. So Sergio, go ahead.
Okay, can you hear me?
Yeah.
I'm new to this platform.
Hi, Sergio.
Hi, Antonio. Very nice talk. Very interesting. Actually, Edson's question brought up a thought that at the beginning of your talk, I thought you were going to tell us how wonderful graphene was for batteries, and then graphene made an appearance.
Sergio, Sergio, are you there? Oh, okay.
Yeah, I don't know. Am I? Can you hear me?
Yes.
Okay.
Yes.
Okay. So what happened to graphene, Antonio?
I got tired of graphene, Sergio. I've been doing graphene for 18 years. I have to do something else, otherwise, the brain goes down the drain.
I know. But I mean, people do use graphene for batteries, and there was all this lithium intercalation, and So if you calculate your, and your formalism, does that give you higher mobility, for example?
Well, we're starting with crystals which have ions in them, right? So you could talk about intercalated graphite,
right?
With ions in it, right? So it's something we're also studying, but we wanted to. This is not something that the industry is looking at. We're trying to look at more traditional materials with cubic symmetry or something like that. Starting from 3D, we eventually get to 2D.
All right. I actually have a technical question, and that is that all of these crystals you have are ionic, of course, so they're very long-range potentials.
Yes.
Do you worry about, screening and those kinds of things?
Yes.
I mean,
exactly. So the thing is that because they are electric insulators, there is no dynamic polarization. You have dielectric polarization in them. Yeah, so this has to be taken into account in the theory as well. But there is no like particle hole excitations, this kind of thing that produces dynamic screening. So the screening is much easier to treat.
But now, once you increase once you have one of these batteries operating, then you'll have a lot more ions.
Yes.
And so their dynamical screening will be important too.
So, by the way, the whole theory here is single ions.
I know, I noticed.
Yeah. So we have not included the ion interaction with the other mobile ions. Right? And we know this is going to be extremely correlated.
Yeah.
Because essentially, one ion is going to repel the other, and you are going to get extremely correlated motion. It's more like, charge density wave motion in an electronic crystal. Yeah,
yes,
I know.
Yes.
We're looking at that. Yes.
Very nice. Very nice. All right. Well, it's a really very nice set of questions. Really. All right. Thank you.
Thank you, Sergio.
Wei Chen has questions. Wei Chen, please go ahead.
Okay. Yeah. Okay. Hi, Antonio. Thanks for this very nice talk. So I have I have a few questions regarding, in fact, just what you have just answered to Sergio, because you say that possibly it can become a charge density wave kind of motion, right? Yeah. And we know very well that charge density wave in the presence of a periodic potential, you have this so-called Fukuyama-Lee Rice kind of physics that, your periodicity can miss one or something like that, can be stacked or. So can you comment on this?
So it's going to be exactly as what you're saying. So, you're going to have phenomena like a creep and things like that, because you have one crystal is sliding on top of another. You're going to have all sorts of interesting physics like that. But again, this is classical. So, it's more like a Wigner crystal is sliding inside of a crystal matrix.
Yeah.
Right. Yeah. So essentially, it's you do have that physics going on there.
But on the other hand, your Langevin equation seems to imply that this is just a Brownian motion, right? Isn't it?
So because we're treating the single ion motion, but in principle, you could write the coupled equations for all the ions, including the long-range potential. Okay. And treat that. It's possible to do that as well.
Can I think of your Langevin equation as like a Brownian motion, but with a driven electric field kind of thing, right?
So it's Brownian motion in an anisotropic medium, where the dissipation varies depending on the direction inside the medium.
And also, I think I missed maybe your explanation. You have an F tilde of.
That's just phonon. This is just phonons.
Okay. So it's like a Brownian motion with dissipation from phonons and also damping and also driven field.
Yeah. And interesting, we can show that this equation obeys the dissipation fluctuation theorem. So essentially, you can relate the fluctuating part with the dissipative part.
I see. And also another technical question, because at the end you inverted your equation and then you get this velocity, right? But it doesn't look like this will satisfy a continuity equation, does it? I mean, it seems like just from that equation, it seems like ions will build up at some location. If your potential is periodic, then it's not translational invariant, right? So
it's only inside of the unit cell, it has to be periodic in the steady state. Yeah. So from unit cell to unit cell is always the same. The problem is what happens inside of the unit cell.
Oh, I see. Okay.
Right. Because the potentials, even inside the unit cell, can be quite complicated.
So it's still a translationally invariant.
It has the symmetry of the lattice. Yes.
Okay. I see. Okay. Thanks for this very nice talk. Yeah. Thank you.
Any more questions? I have a couple. Is it that's kind of in the direction that Sergio was going? Would it be a pipe dream to think that I may find a material or a compound where I can have huge single crystals? That they can be so big that I can have that I can minimize the border effects and this kind of thing, or you are stuck with small single crystals that then you have to figure out how this is going to enter into all the mess that you talked about. How can you? Is there a way of hoping to minimize the mess, and then your theory would be applied directly?
So here's the beauty of this. To make a real solid-state battery, you don't need the mass.
Okay.
So you can actually have very thin solid electrolytes. If they are crystalline, then you can have all the extremely fast battery. Okay? So why you have to put a lot of material on these batteries? It's because you need enough connections for the ions to move from one side to another.
Okay.
And it's a disordered network. But now imagine I make a very thin single crystal. That's all I need. So essentially, you can make batteries in the same way we do electronics. We can do molecular beam epoxy growth of the electrolyte on top of the electrode.
Okay. Like a thin film.
So you make essentially batteries which are films.
Okay. Okay. Yeah. That would
change everything. It changes everything.
That's not a pipe dream, right?
No.
No.
But you see, this was the route taken by the semiconductor industry. That's exactly what they did, making more crystalline as possible, right? And then it's smaller and smaller and smaller. Now we are down to 2 nanometers. But this is because the control of growth of the crystals in the semicon industry is enormous. Right? So you can do the same here.
Okay, okay. My second question goes in the direction of what Edson asked. These zeros of the Hessian reminded me of electrons in a periodic lattice, where the electron will only scatter at the imperfections of the lattice or at the phonons, the vibrations that are dislocations from the perfect periodicity. Does the zeros of the Hessian have some connection with that? Because it's not quantum, right? This effect is not quantum, but it reminds of a quantum effect.
Yes, and but you see the potential that creates this, that is created for the ions comes from quantum effects, because it involves both electrons and phonons. Mm-hmm. So, this is why the electronic structure is so important. Okay. And we have to do ab initio calculations to get that in order to calculate things. Now, the saddle points are essentially positions in the potential where the ion can escape. Because imagine the ion is in a Gaussian potential. It cannot escape from that because it can only oscillate at the bottom of that well. But when you have a saddle point, the ion can always go in the position, in the direction of steepest descent, and leave that position in space.
Okay. Okay.
Yeah.
Okay. This is all very interesting. Let me see here if we have more questions. No, I don't think so. The the DFT people in the audience, do they, are they still there? No, they left. So I want to thank you very much again, Antonio. That was very good reconnecting with you. I hope we stay in touch. And as you said, I'm going to invite you again so that we can follow up on the evolution of that. And I will certainly ask the students to take a look at your paper, because this may have historic importance in a decade or so. Who knows?
I hope so.
I hope so. I hope so too. I hope so too. Okay, so
thank you very much, folks, and have a great day in Brazil. Now it's night here, so
it's time for you to have a rest. Okay, so I'm gonna be writing you an email asking for the slides, and we're gonna, once we post your video, I will let you know.
Okay.
Okay.
Thank you.